Okay, so right now we have device already. So we have a good device, and that is still lots of room to for improvement. But anyway, we have OLED device, and that's similar to LED, so we can use the diode to simulate that. So right now we have a very simplified display, so we can from device to display, how to fabricate display. For example, that's a 4 by 4. We call the dot matrix display. And if we lay down, if we want to have the picture something like that, so what should we do? So that is typically we use scanning and the data mechanism. That is, we scan the row one by one and very fast. So as you can see here, that is the first time frame, then the second one, and the third one, and the fourth one. And then we determine which pixel should we lay down for this row. So for example, this one we need 4, and this one we need 4, and this one we need only 2, and this one we need only 2. So here it's high and low and low. So we can see here, let's take this one as an example. So because here is high, so low to high is blocked. So that is the, and only you can see this one chosen, so high to low. So this one is lit up. Okay, so we call that is passive matrix driving. So that is good for the smaller size, but if you go to the larger size, higher resolution, there will be some problem. Why? Because here we can see if we want to have this kind of the display, this kind of image, then we have the scoring very fast. Right? That's fine because OLED can respond very fast. But the problem comes from, for example, if we want to have the luminance of the 100 nits, if that is 100 nits, and your row number is 4, so which means your peak should be 400 nits. So, for example, we don't talk about 2K, 2K, 1K. If that is 1K, so that would be the 100,000 nits at a very short time. But the luminance of the OLED decrease very quick if you increase the luminance. So when you have a very high resolution or large panel OLED and use this very high peak luminance, and they will decay very fast. So the lifetime is a big problem.
I heard Apple Watch is using passive matrix.
Yes, but it's small.
Yeah, I mean
So
it has only a few pixels.
Yeah, and the main point is the row number. So if the row number is this is the VGA. VGA is the 640 by 480. Maybe. Depends on the row number.
So 640 by 480 is okay?
Is close to the boundary, yeah. Less than 200 is fine. So if you go to Best Buy, and you can see lots of the wearable displays, and that's a very small and very long display over there. That is the OLED. Okay. Because the row number is not too much. And that is flexible. Okay. So that's why we need use the TFT to drive the OLED. And TFT symbol, the structure is something like that. We just go through very quick. So that is like the we can have the three terminals. One is the drain, one is the source, one is the gate. We can use the gate to control the resistivity. So to control the current flow over here. So it comes in like the control the water flow or current flow, something like that. So for example, as we can see, if we change the gate voltage, then here's the current. So like to close, so it's off. And we open, it's on. So we have on and off. So we can use a gate to control the current. Like that. And typically we use two curves. That is the output characteristics, that's the transfer characteristics to simulate the TFT. But I think we just skip here. So that is the simplified is the simplest OLED driving structure. We need a two transistor and one OLED and one capacitor here. Okay. So think that here is the drain. Here is the gate. Gate is to control the TFT open or close, on and off. So let's see what happens when we operate this display. So here connect to your scan line. Here, so it's a row. Here is the data line. It's a column. And goes to the other TFT. Like that. So we say, oh, the scan line we selected. Very short time. Once it is selected, then the data goes in. So, oh, you can use your data. So the function of this one is to switch. And goes in, and they will charge, because there's a current, they will charge these capacitors. So when that is not selected, so it is disconnected, because that is not selected, no function. But because there's a capacitor, so here is a current supply. So the OLED can turn on. Like that. So we need this one to switch and this TFT to drive. So we call that a driving TFT and a switching TFT. And one capacitor to hold the voltage when that is not connected. So that we call the 2T, 1C, two transistor, one capacitor structure. And that is the simplest driving circuit for the 18 matrix OLED. But for the right now the LCD, typically one transistor in one pixel. So in OLED you need two transistors. So that's more complicated. So the difficulty for the OLED as a display, not only for the OLED itself, but also from the TFT. And as we see here, because we need to drive OLED, so we need to provide a current. So the current density is high. But for the LCD, LCD can be modeled by a capacitor. So actually that's the voltage driven, not the current driven. So that is, the requirement is not so strict. So that is pretty difficult for the TFT. Lots of requirement. You need to have a good material, good process, and a good design for the OLED application. So when you consider about the display, right now you have TFT, you have the OLED. So right now you have to consider more. How do you combine these two together? For example, you can put the TFT here, and here is the red, green, blue pixel. So light emit through the glass substrate, something like that. And because right now you need to drive the OLED. OLED is not easy to drive, so you will have a very large TFT. So at that time, maybe 16 years before, and the aperture ratio of this kind of display is less than 10%, which means the emitting area is very, very small compared with the pixel size. So that's why other people think, oh, we can do the other thing. If we need to separate the area, why not we just stick it? So we can put the TFT underneath and use the reflective anode on the top. So it's the first floor, second floor, right? So the OLED can have the higher, larger aperture ratio. But right now, until right now, the aperture ratio is about 50% for the OLED display products. Okay, so there are still lots of the OLED structure developing.
So mainly top emitting is the mainstream for OLED.
For the product, yes. Yes.
Because the bottom emission has much lower or a smaller aperture ratio.
Yes. But also depends on your TFT.
So why does the aperture ratio matter in this case? Why does the aperture ratio matter?
Because if you have the smaller aperture ratio, which means you need to improve your luminance.
Light efficiency.
Efficiency at that time.
Oh, okay.
Yeah. And typically the efficiency drops when you increase the current. Yeah, so if you use a higher luminance, because if the size is smaller, which means the average luminance you need to provide more stronger brightness, something like that. The efficiency drops and nighttime decrease. But typically, for the emissive display, we call OLED is kind of emissive, LED is emissive. So for the emissive display, sometimes from the human factor, sometimes if that is very good and version emitter, sometimes that is not a big case for your human eyes if the aperture ratio is very small. I remember in CRT that is pretty small, maybe 10% or so. But you cannot see the gaps, you still see it's uniform because that's the version. Okay. Okay. And we have about half hour, so let's see how much can we get. So I want to go back to see the energy transfer and singly and triplet. So that is quite a very important thing about singly and triplet and energy transfer as well. So we should go back to the diagram, this one. So let's make this simple. So we just consider 3 states. One is S0, one is S1, one is T1. Okay? Just 3. So when we put the electrical current inside, due to the quantum statistics, Here's 25% acetone. Here's 75% for the triplet acetone. So here is pretty typical for resonance. Here is pretty fast for resonance. So nanosecond, so millisecond or longer, right? So that's non-emissive. And the barrier here is pretty large, 1 electron volt or higher, 1, 2, okay. Say 1 over 1, it's like that. So how can we solve this problem? We can use only 25% for light emission, right? So how can we solve this problem? So there's a way to do that. That is a very important paper published in 1999. They use a material we call the iridium IRPPY3. So it's an iridium inside organic material. Iridium is a heavy metal. And there is an effect we call the spin orbital effect. It's spin orbital coupling. And this spin orbital coupling is more effective when the atomic number is larger. So you need to use something below the periodic table. So for example, iridium. And for this kind of the material, there's some empty orbitals outside. So they can allow the electron goes inside, and possibly there's some change in the states. So although we write the state, something like that, but you still have to consider about that is the potential energy surface, something like that. So actually, you can think about like LED, there's E versus K, but right now it's a potential energy surface. So if this one and this one is well separate, so that's fine. So the electron will go there, there's some movement like that. If they are close enough, there are possibly some tunneling. If there are some crossover, so they can go from this stage to the other stage. So if there are some, if we have some heavy metal and there are some fine structure of the orbitals, so it is possible for the electron, they are in this stage, and maybe from the T state coupled to the S state. So which means the electron is in one state, but go to the other state, just in the just has a different speed. So we can, so that's why they can synthesize this kind of molecule. And that is for light emission, so you have to dope into the host. So what happened in this kind of host doping material? So let's see here. We said, okay, we have 25% singlet. And we have the 75% triplet. So here's the host gas, or anyway, donor acceptor. So they can have the dipole-dipole interaction, so it's a forced energy transfer, and goes up and gives light. And but if that is triplet, then they cannot go stop. So that's heat. Okay? And see here it's different. Here's the dipole-dipole interaction, and this one is the electron exchange. Why? Because it is not possible to go down, right? So that is not possible to have this one. So if your excited state is in triplet, you have to use the Dex energy transfer to go this way, okay? But if right now we have this kind of the triplet, and they can emit the light. So, however, we just transfer the energy. with the dipole-dipole interaction, then they have the intersystem crossing to the triplet because the higher energy, lower energy, and they can have a very efficient intersystem crossing to give light. And for the triplet, they can go through from the Dexter neutron thread, so give light as well. So that is possible to achieve 100% internal quantum efficiency. And the method is something like you can think about this kind of the mixture of the S1 and T1 state by means of the spin orbital coupling. Okay, so that's the phosphorescent OLED. So let's see the device structure first. So that is emitting layer, we know that is a Hall transporting layer. So they can go all the way here and we combine. And here's the electron go inside. And because right now the emitting layer is a little bit Hall transporting characteristics, so you need another Hall blocking layer, or the Hall will go all the way there. So you need another Hall blocking layer. So right now they emit the light. So how do we know it's kind of the phosphorescent OLED, or what's the advantage? So let's see the efficiency. So when they measure the quantum efficiency, so think about that. If we can use only 25% acetone, so it's 25%, and your extraction efficiency is only 20. So that's only 5% EQE maximum. So if you can exceed 5% EQE, which means, oh, maybe this one is better, or maybe this one is better. So if we can have the triplet emission, so maybe this one is better. So you can see here they can achieve 8 in a certain concentration. So if you increase the concentration, they can achieve the maxima, and further increase, they decrease because of concentration quench. Okay? So that is one important breakthrough. And also, I want to address the other one. We should go this one first. Okay. So that was published about 2 years before, and that's we call the TADF. So what is that? Because you know, if we want to have the phosphorescent material, we need an iridium. Iridium is rare, iridium is expensive, and heavy metal, you don't know what happened as an exhaust. So some people say, oh, we are organic. Can we have all pure organic material? To do that, so that is it possible to synthesize the material to reduce the, we call the singlet triplet coupling, singlet triplet splitting. So yes, it is possible. So actually, they just make this kind of molecule, and we combine with two units. One exhibits very strong electron donor characteristics. The other has electron acceptor characteristics. And this moiety is perpendicular. Then from that is possible to reduce this gap and less than 25 milli-electron volts. So that is reduced to less than 25 milli-electron volts. Anyway, you just need maybe less than 100 milli-electron volts. And remember that there's thermal energy. Thermal energy is 25. So that is possible to jump back. So at first, you just spray the acetone, 25% here and 75% here. And so they will give the light very fast. So, but there are some acetone stored here. So they will have the thermally activate because of thermal energy, so they can go back to the fluorescence. But that is very slow, so we say it's a delayed fluorescence. So remember that we say the fluorescence is very, very fast, nanosecond. But for this one, it's a delayed fluorescence up to maybe microsecond. Okay? So that is pretty hot topic right now for the phosphorescent material. For the phosphorescent material right now is used for OLED displays. And the TADF material is new, so they are still developing some kinds of the materials. And that is, for the phosphorescent, that is very successful in the red and green OLED. But for the blue, that is not so good, because for the blue, we said the energy is too high. So typically, the lifetime is a big problem. And consider about that, for the phosphorescent material and for the TADF material, the lifetime is super long. So which means the molecule at excited state has a very long time scale. So which make the lifetime even worse. So right now in the commercial products of the blue OLED, it's not a phosphorescent, not a TADF. But if you use the fluorescence, that is too bad. So there's an alternative one. We call the TTM material. So that is for the, right now, commercial blue OLED. So what is that? That means, so the T is always less than S. You cannot change that because that's from the basic theory. So why not we just reduce it the T very low, ultra low, over here. So maybe I don't have the talent to have to do some to have my degree. So why not I just forget about it? So I go to earn some money. So after I earn lots of money, so I can buy the degree like that. So okay. So let's see here. So right now it's the same, 25%, 75%, right? To the SNT, that's no change. But that is super low, as low as maybe 2T equals to S. So possibly 2T can have 1S. So we call that a triplet annihilation or triplet fluorescence. So that is what we use for the commercial products. So we use 2T and become 1S. And triplets is slow, but singlet was fast. So they can achieve the acceptable efficiency. Is there any energy loss in this structure? Is that as good as phosphorescent or TADF? Yes. Huh? You need 2T. Then you can have only 1S. Okay? So that's your loss. So you lost in efficiency. So your efficiency is limited because here give you $100 and the 25 bucks you can emit the light, and 75 bucks and you can. 2 of this one is needed to convert to 1 single. So there's an intrinsic loss. So the efficiency cannot be as high as the phosphorescent, cannot be as high as the TADF, but it's alternative. But they have a very fast decay time, so they can have the higher lifetime, especially for the blue, because the blue band gap is larger. Okay?
The EQE is still 10.2% compared to like a 13.4 for TADF. That's not too bad.
Yeah, correct, not too bad. So that is the homework problem. What's the theoretic limit of, I should say IQE, right?
It was in-
Yeah.
Internal quantum efficiency, not external, forget about the external, internal, just internal.
And how would that apply to the homework question then? As far as, the homework question was, what is the theoretical internal quantum
Internal,
efficiency
internal.
for triplet annihilation?
Yeah, so for example, for the phosphorescent or for TADF, that's 100%. And how about for the TTA? Okay. So, So, for example, for the fluorescence one, so only 25%. So we assume the triplet, that this row is blocked, okay?
Right, because in that one, the triplets donated nothing.
This one? You mean the TTA?
Yeah.
And that one,
For the fluorescence, yeah, the triplet donate nothing.
right.
And for the phosphorescent material,
Right,
because that is mixed together,
right.
so that's 25 plus 75%. So that's 100.
So that's 100, right.
So that's the same for TADF. So my question is, how about the TTA? Because right now, for the triplet, they have other way to go back to singlet. So what's the,
Would it be 32.5 plus 25?
37?
Yeah.
What's that?
75 divided by 2, that's 37.5.
Plus 25?
Yes. I can tell the answer. Okay. So, well, simple, right? Yeah,
Hope everyone gets it right.
yeah, but anyway, actually, from some calculation, they say because there are some, for the triplet itself, there are some different energies. So from some theory, they say not every triplet can meet together to back to the singlet. There are still some splitting. But anyway, right now I saw the EQE value is pretty high, so I'm not quite sure because there are possibly not some issues inside. Okay, so anyway, here I want to address the singlet triplet problem is very important for the OLED and not for the material, also for the device, and we need to carefully design our molecules and devices as well.
So this TTA doesn't need those iridium. Right?
No.
Yeah, so these are simpler, well, not necessarily simpler, but just regular organic.
Yes, pure organic. Yeah.
Does it affect lifetime as well?
Yeah, the TTA, the lifetime is longer and is okay for the commercial use for the mobile phone right now, but still shorter than the phosphorescent green and red. So the band gap does matters. Yeah, so think about some way for the TTA material, and that is mature because that was developed for about 10, 20 years. So how can we do some trick to make there's no energy loss? So that would be good. Okay? Okay, so we just said this a little bit about material. So we just talked about the TADF. You need one molecule, and that consists of two moiety. One is electron donating group, one is electron accepting group. So some people say, oh, that's too difficult to combine these two molecules together. To combine these two moiety to become one molecule. So why not we just physically mix them together? So that's their way. So they mix the donor and acceptor material. So they form the exciplex. Remember we say it's a donor and acceptor formed together. So they can achieve the very high efficiency. For example, EQE higher than almost 30%. Yeah. So there are lots of interesting research in these topics.
What's the drawback?
What is the drawback?
Yeah, I mean, it has such a high EQE, right? Why not use it?
Oh yeah, because right now the material here, the lifetime issue still a problem. Yeah. But right now, I think maybe these 3 years, there are lots of the exciplex emission. So possibly there's another way, because the effect is similar to TADF, but you don't need a new material. You don't need such a very difficult material. You can have lots of choices. So it's also emerging topics for the exciplex emission. So here is for example, it's a mixture of these two materials, NCP and the P3, PY, and PN, so it's very long. So you can see it's the PL for the MCP, and this one is the PL for this material, and if you mix them together, they have even the redshift. So that's the sign of the exciplex. Yep. Okay, so we still have some time. I want to address about the lifetime, because lifetime is one of the biggest issue for the OLED. So there are typically two lifetime. We talk about one is the operation lifetime, the other is the storage lifetime. So that is typically lifetime chart when we use measure the OLED. So we use a constant current. So constant current means we provide the same electron hole pair into the device and observe their luminance. So which means your efficiency decrease. So the luminance decrease means the efficiency decrease. And the other thing is because we use a constant current and we can monitor the voltage. So the voltage typically increase. So which means the resistance of this device increase. So because right now we say, oh, we need to use 1 year, 2 year, 10 year. So it is typically not easy to measure for such a long time. So we use that acceleration measurement. For example, we can increase the luminance, or we can increase the temperature, or something like that. And if you want to know the operation lifetime itself, typically we use a higher luminance. So, for example, if we use a higher luminance, 12,500 nits, then they will decay pretty fast. So you can measure in 5 hours or so. It's blue. So if you increase to 10,000, if you decrease the luminance to 10,000 or so, then you can see the half-lifetime increase. Half-lifetime means they go to the 50% of the luminance. Okay. So let's see that. So we can see if we plot the initial luminance versus half-lifetime, and you can see, oh, they're beautiful line over here. So you can say, oh, in 2000 nits, maybe you have the almost 2,000 hours lifetime, and 1,000 nits, and 15,000 hours lifetime, something like that. And in this line, you can obtain the equation. For example, luminous times to half-life time to the power of n. So for example, in this line, n equals to 3. So what does that mean? That means if we have the for example, if that is the 100 nits, right? And maybe, oops, is that correct? Oh, that is not correct. 3 is here. Not here. Let's change that. This 3 is over here. And we want maybe 100,000 hours, we hope. Like that. But if we use the, so that's the display we want, 100 nits, right? So if we want to use the passive matrix, okay? So if that is passive matrix, maybe 1K, assume that's 1K. So that would be 1K nits to the power of 3. So that would be ultra short, right? So just 1 hour. Okay? So that's a problem for the OLED operation lifetime. If you increase the luminance, typically lifetime decrease a lot. So there are lots of mechanisms to explain that. I think we don't have time. So I want to address another thing is the storage lifetime. So that is a picture under the optical microscope, and they fabricate this device. And before the cathode evaporation, so after the organic, but before the cathode, they spray some SiO2 sphere, then deposit the metal. Then there are some, so the oxygen and the water can go into the, from some space to oxidize the cathode. So you can see there are some non-emission area under the microscope. And it grows up. So from 5, 10 seconds, 9, 60 seconds, so you will see the dark spot grows and grows. So that's electroluminescence. That means you supply the electrical current and observe the luminance. So here is dark, outside is bright. But if you use the photo excitation, that's no good. So which means cathode is a big problem for the operation lifetime. The oxygen and the moisture, typically they will attack the cathode a lot. Okay?
I have a question regarding to the definition of lifetime. Some literature or people, they use T95, 95%. And some use T50, some use T80 or 85. Which one is more representative?
That depends on the what you want to see. Depends on also the application, also from the theory. Okay, so from the application, as typically we said display or lighting. Okay, so for the display, if the luminance difference is about 5%, then which means people can see that. So if there's a luminance 5%, you can differentiate that. So that's the start point of the image burning.
Okay. So
Yeah.
that's a T95.
Yeah, so that's a T95. But for the lighting, actually, we don't know.
Yeah, it's uniformly dying.
Yes, so we don't know. So that's maybe T80 is usable. Yeah. And sometimes for the T50, we like to see the different degradation mechanism at different stage. Because sometimes we see that is not only one slope, there are different slopes. So we need to analyze which time accounting for the short-term decay, which time accounting for the long-term decay. Yeah, so it's different.
And that's one. Another is like a differential aging between different colors.
Oh, yeah, of course.
Yeah.
Yeah, so that's also related to the how you fabricate the OLED. You can fabricate a red, green, blue OLED separately, or you can use a white OLED, use color filter. So for the TV, right now they use, for the TV, for the company, they prefer to use a white OLED with color filter because the differential aging is
Yeah.
less significant. Yeah.
I mean, for the like a listed number of lifetime, how many hours, how many thousand hours, are those in material, I mean device level or in the panel level,
Device level.
device level?
Yeah.
I mean, LG is never disclose any lifetime of their OLED TV. Do you have any insight?
It's recorded. Put on YouTube.
Okay.
Yeah.
I'll ask privately.
Yeah. But anyway, of course, there are some lifetime issues. Yeah.
They never mentioned that. Probably they don't want to scare away the customers.
Yeah.
I mean, very insightful lecture. Well, thank you very much, Professor Lee.